So the things that we've been doing in 6.2 and 6.3 or 6.3 and 6.2 are specific to the normal distribution, okay? If you remember when we talked about binomial experiments and binomial distributions, we can actually use the same strategies that we've been using to also come up with some binomial probability type situations, okay? But there's certain criteria that we need to follow before we can do that and establish before we can do that, and that's kind of what we're going to talk about. First off, here is when we're talking about a binomial distribution. You can write all this down, you can take a picture, it's up to you. But remember all of these things that we had to check for first in order for it to be a binomial distribution.
What lesson is that one?
So remember, each trial can only have two outcomes, a success or failure, and the situation will determine whether something's a success or a failure. There must be a fixed number of trials. The outcomes must be independent of one another, and then the probability of success has to remain the same for every trial. Okay, and yeah, this was back in chapter 5. Okay. So here, remember this? We had X represented the number of successes, N was the number of trials, P was the probability of success, and Q was the probability of failure. We need to use all of this still, and this is what's going to allow us to now use the normal CDF to find the probabilities of these binomial experiments. Now, that being said, knowing that we have a lower bound and an upper bound, that's where it's going to get a little tricky, okay? Establishing the right boundaries. And part of what we're going to be doing today is learning how to correctly identify our boundaries. The other thing is that just like we had to ensure that it was an actual binomial experiment by making sure it met all that criteria, there's some computations that we need to do before we can use the normal distribution to approximate the probability of a binomial experiment. Okay, and so that's part of what we're going to be talking about now too. So every time we have a situation like this, and we want to use the normal distribution to approximate the binomial probability, we have to check to make sure we can proceed. And here's what you have to do. Okay, this you definitely need to write down. And those are supposed to be multiplication, n times p greater than or equal to 5, and n times q greater than or equal to 5. Then you can use the normal distribution to approximate the binomial distribution, meaning that probability, okay? And every time we do this, we have to show this. We have to take the actual steps to multiply n times p and multiply n times q and demonstrate that, yes, those products are indeed greater than or equal to 5.
So you can use normal CDF, that's normal CDF, right?
Once we do this, then we're going to be able to do normal CDF, yes. Okay.
So that's basically saying then
the normal distribution is normal CDF,
okay.
Yes. I'm just going to add one more thing up to this. You have to check for this and you have to show it. You can't I just did it in my head. N times P, yeah, it was definitely greater than or equal to 5. You literally have to write it down. I know it seems like a small thing, and most of the time you're going to be able to do that multiplication in your head. I get all that. But you really can't even proceed until you do that. And you have to write it down and you have to show it. Okay? And when we go through an example, you'll see what I mean. It obviously doesn't take much to do. And as soon as you show that product n times p and the product n times q, and that they're both greater than or equal to 5, then we can go forward. Okay. Now the question inevitably comes up is like, well, what if it doesn't? Then what do I do? Then you have to find probability the old way, and the way that we did it in chapter 5 for that situation. Now I'm going to tell you that most of the time, I'm saying most only because I don't remember off the top of my head. I'm pretty sure there aren't any. I think they're all going to work out, but you still have to show it. Okay. So let's go through a situation now. Here's where we get into the intervals and where this gets trickier, okay? Because it's an approximation. We are approximating the probability using this other method, okay? We have to use something called a correction for continuity. when we enter it into our calculator, and that's where we learn how to write the boundaries. And you'll see, yeah, no, wait, there's gonna be something else down here, and then you can take a picture of it. Now, before I put this on the screen, I want you to understand that you can choose to memorize what you're about to see. However, I'm gonna try to come up with a way that I think makes it easier to reason through, so you don't have to memorize something, okay? And if you can think through it a little bit, I think it makes it a little bit easier. But here it is, okay? And we have 5 cases. Okay, there are 5 cases. And I'm going to talk through all of them. If you look to the right, notice there's either a plus or minus 0.5 all the way down, okay? And I'm going to explain why one is added and why one is subtracted here in a minute. Okay, but that's the correction that we make, is that this by a half a unit, I guess. Okay. The other thing that, and this comes back from chapter 5 as well, that we're going to talk about, because in order to do the normal distribution, right, we have our boundaries, but then we also have the mean and we also have the standard deviation. And if you recall from binomial experiments, the mean was n times p, which you're already going to have to do that multiplication anyway, right? You can't even proceed until you do that, because part of what we have to do is this right here to prove that n times p is greater than or equal to 5. So even before we can proceed, we've actually already found the mean. Okay. Now the standard deviation, of course, you're going to have to take n times p times q under the square root, since standard deviation is the square root of the variance, because n times p times q is the variance. So those are the calculations you're going to have to do, and what we're going to do on the next slide is I'm going to show you, I think, a better way of thinking through how to come up with the boundaries. Okay? Questions so far? Can I move off this slide? All right. So we're going to go through 5 examples, and I just chose 7 because why not? All right. So we've got an equals, we've got a greater than, we have a greater than or equal to, we have a less than, and we have a less than or equal to. And understand that the correction is always going to be 0.5 when it's an integer. Okay, so if it was to the 10th, then the correction would be 0.05. If it was to the 100th, like 7.77, then the correction would be 0.005. So we're tacking an extra decimal place that is a 5 to the end of whatever you're given. Okay, in these situations, more often than not, you're going to be given integers, so it's going to be plus a 0.5 or minus a 0.5. And what I want to talk to you about is how to decide which one we do. Okay. So this is so I'm setting it up so that I can create the lower and upper bounds for each situation, and so that when you encounter a situation like this, you're going to have to decide, because they're going to be nothing but word problems, right? So you're going to have to decide based on the problem, is it equals, is it greater than or equal to, is it less than or is it less than or equal to? You're going to have to figure that out from the context of the problem. Now, most of the time it's going to say, word for word what you're supposed to use. But here's the goal, okay? The goal is to make sure that whatever set of intervals we come up with, that either the number is included in the interval or it's not. And based off of what it says, it tells us whether or not it should be included in the interval that we create. For example, okay, when it's equals, it's easy. You add a 0.5 and you subtract a 0.5. And that way we guarantee that 7's in that range. Okay? So for the equals, it is worth memorizing. Look, I got to add a 0.5, I got to subtract a 0.5, and that's my intervals. It's pretty straightforward. Okay, so for my interval that I'm going to use, my boundaries that I'm going to use when I enter that in to the calculator for the normal CDF, I take it down a tick by 0.5 and I go up, and I guarantee now that 7 is obviously in between 6.5 and 7.5. And because it's approximation, that's why we use that range. Okay? So the equals one is easy, right? And so when I would enter this in, my lower boundary would be 6.5, My upper boundary would be 7.5. You have to figure out the mean, you have to figure out the standard deviation, hit enter, done. Okay? Any questions on that one? Now, this one is where it gets a little trickier, and I want you to think through it a little bit. Okay? This inequality is saying x has to be greater than 7. So the question becomes, is 7 part of this interval? No, it is not. 7 is not part of this interval. It has to be bigger than 7. And here's what we're doing. We're adding a 0.5 or subtracting a 0.5 based on the situation. Since 7 is not included in that, I need to go bigger than 7, which tells me I need to add 0.5. So what I end up for my interval is just greater than 7.5. And what we end up with, since 7 is not included in that either, I'm going to end up with 7.5 as my lower boundary and 1, or positive infinity, 1 times 10 to the 99th as my upper boundary, okay? Since it's greater than. Now, for the next one, is 7 included?
Yeah.
Yes, it is. So instead of going above where 7 is excluded still, we go down by 0.5. Then, everything greater than 6.5 does include 7. We do want 7 to be part of the interval, so we back it off by a tick. Does that make sense? Okay? Now, again, I'm telling you, if you want to memorize the chart and know I got to add when it's this and subtract when it's that, you can do that. But for me, it's easier to be honest. I think through it. Is the number in there? So how can I create an interval so the number that we're talking about is actually in the interval we need? Okay? So why don't you go ahead and try the last two and see what you come up with, and we'll decide if you did it right. Again, the reason why we're doing it as 0.5 instead of just using the actual number is because it's an approximation. So that's that correction of continuity that they talk about. So we're making a little bit of a correction to.
So it's like calling that one wrong.
Well, technically, you aren't supposed to use the normal distribution for a probability experiment. But what we can do is adjust it just enough so that it does become reliable.
So this 0.5 is the smallest you could adjust it?
Well, since my numbers are integers. Okay? Alright. How many of you have the next two, you think? Raise your hand if you have the next two intervals. So for this first one, x less than 7, is 7 included? Okay, so what number do I need to move to make sure that we exclude 7? 6.5. Okay? So it's going to have to be less than 6.5. If you said less than 7.5, you included 7 in the interval, right? And we don't want to include 7 because it's not or equal to.
So
Now go ahead.
Wouldn't the next one be x is less than 7.5?
Yes, because we want to include 7. Okay, because this is or equal to and we want to include this number, we actually go above it since it's less than. And then x less than 7.5 includes the 7 in the interval that we need. And so all 5 of these intervals that we've created, we've dealt with at some point when we've plugged it into our calculator to do normal CDF, right? You've got negative infinity, positive infinity, or in the case of the very first one, you actually have an upper and lower boundary, okay? Are there any questions about that? This is going to be a big part of your success and or failure, is creating the boundaries and intervals properly, okay? The rest of it's not going to be that bad. So you're not going to be given all of these. One of these things will occur per problem, and it's going to be up to you to distinguish which one it is, okay? So, and that's what we're going to do next, is actually go through a problem. So, go ahead if you want. It's in the book on 343, and, or you can take a picture of that, and then we're going to work through this problem, and that's what we're doing to finish up this lesson. First off, you actually have to go through the process of deciding if this could be a binomial experiment, meaning there's a fixed number of trials, there's same successes and failure percentage or probability, that the outcomes aren't affected, they're all independent, you really have to go through that, but we're gonna just assume that that's the case here, okay? What we do need to do is make sure that n times p and n times q are both greater than or equal to 5, okay? And that's really the first thing we have to do. So we have to find those things. So go ahead and do that. N times p and n times q, and see and make sure that they are both equal to, greater than or equal to 5. Number of trials. N is number of trials. In this case, what is the number of trials? 200. 200. We're sort of surveying 200 league members, right?
And P is
Point one.
Your success, yeah. And
Yep. So the success in this case is that they're a widow, and the failure is that they are not.
Oh.
Okay.
And then Q would be
That's
0.9,
pretty messed
right?
up. If you ask me.
Well, yeah.
You know, the other thing that I would say, now that I think about this, I know it says widowed bowlers. It could be male or female. I know we call females who have lost their husbands widows, but we call males who've lost their wife widower. And we wouldn't say widowered. So you could be widowed as a male or a female.
We call males widows.
Yeah, if you're a male who has lost their wife, is not lost, but their wife died. They are a widower. A wife whose husband has died is a widow. Okay. Anyway, but I digress. So, what is n times p? 20. Okay. So 200 times 0.1 is 20. Then n times q? 180. Okay. So, they're both greater than or equal to 5, which means I can proceed, okay? And like I said, you have to show this every time. And that's the next thing it's going to say. Both are greater than or equal to 5, so the normal approximation can be used. You don't have to write that in green. What I put in there in green, you don't have to write down. I know that you can look at 20 and 180 and know that they're bigger than 5, and now you can keep going. So when you get to your problems, when you get to your test, you need this over here. I don't need you to write that. I'm just giving you my justification for why we can keep going. All right. Now, the next thing we need to do is come up with our interval. Okay. So we're looking for the probability of what?
But
10
or more.
10 or more. Which, so if I wrote that as an interval,
Is X 10?
well, let's just start with the probability of what we're trying to find, and then we'll work on the interval.
like this.
So what is the probability of?
It's gonna be greater than 10.
The other way?
Can it be equal to 10?
Yeah, it says 10 or more.
Okay, so the probability that we're looking for is x is greater than or equal to 10. So once we determine our probability, because it says 10 or more, we'll be widowed. So 10's included. From there now we can create the interval using that correction, that 0.5 correction. All right, so go ahead and do that. But what's the interval that I'm going to use here?
X greater than
It's on your right sheet.
Greater than 9.5. So we include, so we're going to include 10 in that boundary. Okay, so the bound is greater than 9.5 because 10 is included. All right, now the next thing that we have to do, so we can write that like we did before. So we need the mean, and now we need the standard deviation. And the mean we've already figured out, right?
What's a mean?
The mean is n times p.
Oh.
Okay. So what is it?
20.
20. Okay, so the 20. Now I need the standard deviation. And the standard deviation is the square root of n times p times q. And before you get ahead of yourselves, all right, I want to be very clear about something. I do not want you to approximate this decimal and use a decimal. I want you to put an exact value in. Okay? And for that matter, you could leave it as n times p times q. I don't think you should do that. I think you should actually just multiply those out because it's just not that big a deal. Okay. So we already know that n times p is 20. So this much right here is 20. Now I just need to multiply it by q, which is 0.9, which we already had to use q before anyway. So in reality, what I'm doing, I'm taking 20 times 0.9, which is the square root of 18. And we're going to use the square root of 18. This is what I'm saying. You could plug the square root of 18 in your calculator and it'd give you a irrational number, a decimal that's never going to end, it's never going to repeat. You could do that too, 3 square roots of 2, that's fine. I'm saying you can leave it as the square root of 18 and use that as your standard deviation when you plug it into the normal CDF. Right? That's my preference, is that you use the exact value. Now if it simplifies to an integer, you're welcome to do that too.
So what if it?
I have everything we need now, okay? I have the boundaries, I have the mean, I have the standard deviation, normal CDF, go for it. Finish it. His question was, is this a sample situation so I could divide the standard deviation by the square root of the sample size? The answer is no. We are not worrying about that for this, okay? For using the binomial, for using the normal approximation for a binomial experiment, we don't worry about sample or population. We don't have to divide the standard deviation by the square root of the sample size. That doesn't come into play here. So here's what you should have had boundaries, okay? Since it's greater than 9.5, that means 9.5 is the left boundary, positive infinity is the right boundary, my mean is 20, and my standard deviation is the square root of 18, and I want it left there. That's what I'm saying. Don't put a decimal in there. Okay, how many had that set up?
Wait, so why don't you do the radical 18 over?
Because for this approximation, we don't worry about that. It's just not necessary. Okay? Alright, so here's what you should have gotten. 99.33%. So, let's think about if that makes any sense, okay? Because that's obviously, it's like almost guaranteed, right? That 10 or more are going to be widows in this bowling league of 200.
Nice. That sounds good.
Alright? Well, and here's why that number is so high, right? If we believe the premise that 10% are widowed and 10% are 20, right? 10% of the entire league is actually 20 people. The probability that it's 10 or more should be very high because we actually expect it to be 20, not 10. So that's why it's so high. It's because 10 is low. Now, if we would have said, what's the probability that 25 or more or 30 or more were widowed, we'd expect that number to be a little too high, therefore the probability would be a little smaller. Okay? Does that make sense? Contextually? Okay? Alright. There you go.
Do you want to